YouTube. In this video we will discuss how Laplace can help us solving the differential and integral equations. Okay, so first of all I'll give you a very easy question, that is how you will solve this equation x plus 2 equal to 4. Okay, and you are so happy to solve this and you'll get the answer x equal to 2. In the next equation I'm giving you this equation, x square plus 6x plus 9 equal to 0. Again, you are really smart and you can solve it within seconds and tell me the answer is x equal to minus 3 and minus 3. So this is called the algebraic equations. But now this is a tough one. Solve this equation, d square x upon dt square plus integration of 5 dx plus 6 equal to 0. Okay, so now you have to think something, because solving this is not really easy. Although you must have studied in your engineering classes that there are three methods to solve this. The first is the Laplace, second the Fourier, and the third one is classical method. In this we will discuss about the Laplace transform. So Mr. Laplace, he thought, okay, so you are good in solving algebraic equations. Why don't I convert these integrals and differentials into algebraic equations so that you can solve it? And he helped us. Let's see. So Laplace converts these equations into algebraic form, in which you are good at and you can easily solve them. Let's take an example. In this case you have this Laplace, you have this circuit with the capacitor is charged to voltage V, R, we have a resistor connected in series, and we have a switch. At t equal to 0 we will be pulling this switch. So first we will convert this into a equivalent circuit. In this I am taking the voltage out of the capacitor just for the sake of simplicity, and here we have the circuit with the current IT flowing in it. As soon as you close this circuit, you can apply the KVL. V is equal to 1 upon C I dt, that is the voltage across the capacitor when current I will flow through it, plus IR. Now you cannot solve this because there is an integral, so you ask Mr. Laplace for help, and Mr. Laplace says, don't you worry, take the Laplace. Okay, so we take the Laplace and Vs equal to 1 upon Cs Is plus IR. So we see that this integral has been converted into S. That means you have converted this integral equation into the algebraic equations. And so now you are interested in the current. So if you take the current on the left hand side and solve the circuit, the equation comes out to be like this. And after you take the inverse Laplace of this, you will get an answer which is equal to something like this. Okay, so this is the answer. So this is V upon R e raised to power minus 1 upon RCT. V upon R is something, the answer that you will get if there is no capacitor in it, and this is decaying continuously exponentially with time. So if you plot the curve of IT, you will see that when t is equal to 0, when you put t equal to 0 here, this term becomes 1, and there is a t equal to 0, this term becomes 1, and you have a maximum current flowing at t equal to 0. But after, as you keep on putting the value of t equal to 1, 2, 3, the current decays and eventually becomes 0. So let's take some values. I will be putting the values of R and C in this portion only, and then I will calculate the percentage of current at that particular instant of the maximum current. When I take the value of capacitor equal to 100 microfarad and R equal to 1 mega ohm, at t equal to 5 seconds, the current is 95% of the maximum value, and at t equal to 10 seconds, the current is 90% of the maximum value. And if I put C equal to 1 farad and R equal to 1 mega ohm, although you will not find such a big capacitor in the market because they never make that, 1 farad is a very, very, very big value. And at t equal to 5 seconds, the current is almost 99%, 99.99%. That is almost 100%. At t equal to 10 seconds, the current is again 100%, 99.99%. So you must have listened that the capacitors block DC. But if you compare the values here, the capacitor is not blocking the DC. At t equal to 5 seconds, the current was 99% of its maximum value. At t equal to 10 seconds, the current still is 100%. So within 10 seconds, if the current is big enough, that can kill you, yeah? So this is actually the real answer, because that is a transient. For a very short amount of time, the current actually flows in the circuit, and after t seconds, the steady state comes. And in the case of steady state, then the current becomes zero. So if you want to see a practical circuit, something built on this, you have to see my another video. Just click on the subscription. And eventually I'm looking at ways to use Laplace in my LED cube, how I can solve this LED animations using the Laplace, and my Zigbee's pretty little trans receivers. They have a very good range, cheap, and I'll be soon making a projects using these. Thank you very much. Bye.